can use, it's not a problem.
I prefer to write.
So we have like a here. Let's move up and down. And then we have the projector. Turn off.
Should you stop it in correct moment or just?
No, just move up and down.
Okay.
And it will go in the right place.
Okay. Okay.
So
thank you.
Just a second. I will introduce you. How do I correct say your last name?
Mirzayanov.
Mirzayanov. It's streaming, so.
I understand.
Okay. So welcome everyone for our second week of summer school, and it's a pleasure for me to introduce you to Mike Mirzayanov. I know most of you already know him, so thank Mike for being with us, and I hope you all have a very nice week. Thank you again.
I hope too. Thank you very much. I'm very glad to see all of you here, and maybe probably most of you know me because of Code Forces, but here I'll be your teacher and we will cover many topics about strings algorithms, and also as your regular schedule you will have contests, and here we will discuss how to solve the problems. Okay, let's start with string algorithms. Actually it is very huge topic, and there are many different interesting algorithms in it. So, and I ask you to hear each my word, because you know, if you didn't understand some items at the beginning, it will be difficult to understand maybe some topics that we will cover tomorrow or in other days. So I hope that it will be interesting for every of you. Actually in Saratov we have maybe some kind of similar training camp, Sazanka training camp. It is in nature, in the bank of the river, and every 2 years we cover strings algorithms in this training camp. So here it will be some kind of short version, because there are 10 days there but only 5 here, so it will be some short version maybe of lectures that I made there. Actually it is my first time I'm doing lecture in English, so I apologize for my English maybe, but if you do not understand something, feel free to raise your hand and ask for details and something else. Okay? And let's start. We will start from the very beginning and we will talk about strings. Strings are just sequences of characters. We will use zero-based indices almost everywhere. So string S is just S0, S1, and so on, Sn minus 1. We will use absolute value for S as length of a string. And the correct way to think about strings that it's not only about texts, because for example array of integers is great string, and also array or sequence of objects of any nature can be treated as a string, and you can use the same algorithms as we will discuss today. Okay, there is one specific string, empty string. It is allowed, yes, the length is 0. Okay, also we will use to definitions, prefix and suffix of a string. Prefix is just some first characters of a string, and suffix is last characters. So prefix is this prefix has length I, and if we are talking about suffix from position I, it is just last characters of the string. We will use the term proper, prefix or suffix, if it differs from the whole string. So formally the whole string is suffix, and also it is a prefix. But if we are talking about proper suffix or proper prefix, the whole string is not. Okay. In recent years, this area of knowledge called stringology grows very fast and efficiently because of connection with genetic algorithms, microbiology, and so on. I'm not good in it, but most books about string algorithms are not only about math and computer science, but also about biology and so on. And here in this topic, the main problem is string searching problem or string matching problem. Everybody know it, and you often use the solution of it while, for example, if you press Ctrl F in your browser and type some text, the browser solves the matching problem. You have some usually long text. It is a string, and also you have pattern. Usually pattern is shorter than text, and what you need is to find all or maybe some, or maybe to check if it exists, occurrences of pattern in the text. I mean, you should to find such substrings of text which are equal to the pattern. In this example, the text contains two occurrences of the pattern, and right now we are speaking about very simple patterns which does not contain any special characters like wildcards and so on. So the text and the pattern, they contain only regular characters from alphabet. Usually in these problems we consider that alphabet is finite, but actually some algorithms do not use it because you just compare symbols, compare characters, and nothing else. Okay. You know that many programming languages have native API to solve this problem. For example, str function in C++, index of in Java, member function pause or find for standard string in C++ and so on. Actually, most of these implementations do not use some clever algorithms and use just naive approach. What is naive approach here? Just imagine that occurrence start from the 0 position of the text, and let's try to check character by character for the first mismatch. And if we find any mismatch, then let's try another position, the next position, and so on. It is easy to see that naive algorithm works in time order of n multiplied by m, and could be very slow on large texts and large patterns and so on. But actually the most tricky thing that in real world data, in real world text and so on, it is a very rare case, because if you choose random position in text and this position is not the start position of occurrence, you will find the first mismatch very fast and so on. But if we build special tests against this algorithm, it is easy to see that we can use, for example, long string containing only letter A, and as a pattern we can use, for example, long string containing letters A and letter B at the end, and each check will make m iterations, so it will be exactly the same complexity. Okay. There are two different ways how to deal with this problem. The first way is to pre-process the text. If we have the text and, for example, we have patterns as queries. If we have patterns, many patterns, and we should reply for each pattern if it contained in the text or not, it is a good approach to pre-process the text, and after it, somehow, we do not know how exactly right now, to answer for the requests about is pattern inside the text. And the opposite way is to pre-process patterns. So we can pre-process the pattern, and after it we will have easy way to check for pattern. Does text contain it or not? For example, if we speak about something like search engine or something like this, what way is the better? The first or the second? What of them? What is better, to pre-process the text or to pre-process the pattern? No. We should pre-process the text. The text is our data, our websites, and so on. And we have a lot of small requests from users. And each request is pattern. Find me, pattern says. And you should use pre-processed the text, and text is very, very, very large. It is very, very long. And but actually, if we compare two ways, the first way is more tricky and more interesting. Maybe we will discuss it, and I hope that we will discuss it in next days. But we will start our lectures from pattern pre-processes. So our idea is to pre-compute something in such way that it will be easier and it will be faster to check does text contain the pattern. Okay. Oh. And the first idea I'll cover, it will be idea of Z function. Z function of a string. Z function of a string, it is not concrete single value, but it is an array. It is an array of lengths equals to length of the string. So if you are given string S, we can build that function, and it is an array. And it is such array that the value in position 0 is always 0. And the value in any other position is the length, longest common prefix of string itself and suffix which starts from the position I. It is the definition of that function. Let's look into some examples. For example, if string S is A, B, A, C, A, B, A, it is very famous string. Such strings are called gray strings. I don't know how in English to pronounce correctly them, but in Russia we can pronounce them very fast. A, Aba, Abacaba, Abacaba, Dabacaba, Abacaba, Dabacaba, Yabacaba, Dabacaba, Abacaba, Yabacaba, Dabacaba, Abacaba, F, and so on. Each next string is just 2 copies of previous string and next alphabet character between copies. You see, they are very symmetric, they are very interesting, and actually you should check every your string algorithm implementation on strings like gray strings. Okay, and let's calculate the Z function for this string. Okay, Z of 0 is 0 by definition. Z of 1 is 0 because no common prefix of the whole string, and string started from the position 1. But if we look on the position 2, I think the answer is 1 because the length of longest common prefix is 1. Here we have 0, and here we have what value? 3, right, 3. Actually, I like some interaction on my lectures. Maybe it will be difficult a little because of English and so on, but let's try, okay? And if I ask something, it's okay to give me the answer. Okay, and here, what is the value? 0, and the last value? 1. Okay, it is that function. Another example. If S is A. That function is 0, 4, 3, 2, 1. You see. Actually, most algorithms which use that function, they do not use the first position. And in some, you can think about it as it is undefined, actually. But it is possible that personally for your problem, maybe, it will be better, for example, to use value n instead of 0, because it is natural, right? So feel free to use 0, n, or just undefined value as z of 0. It's okay. But this definition is some kind of classic here. And I use it because of it. Okay. And no, for example, the last example, AB, AB, AB. Okay, 0, I think 0, right? 4, 0, 2, and 0. Am I right? Okay. Some kind of magic. I do not have such boards, blackboards in my university. Okay, and it is a question. Why actually we need it? Why we need some Z function if we speak about string matching problem? They do not like very similar this function and the problem to find pattern in the string. But actually they are connected, and that function can be easily used to find occurrences of pattern in text. Have the form. First, we will write pattern. After it, we will write some special character, and we will call it separate. It is some character which is not in P and is not in T. For example, we can extend alphabet for one character and use it. In practice, in my solutions, I prefer to use something like character, this code 1, for example, just a separator. It is non-printable character, and for sure it will not be in any strings. Okay. Let's return to our example. A, B, C, sharp. Here is an example of string S. And let's calculate the function for string S. We will not calculate it manually one by one, but it's easy to see that in this position and in this position, in these two positions, that value equals to 3. And it means that 3 characters here are exactly the same as first 3 characters. And so here the same. So if we have, if we want to find pattern in text, we can build this kind of string, calculate the function, and if for all such values of that function that equal to length of pattern, it means that I is starting point in occurrence. But right now we do not see easy way to calculate that function. If we use definition, it will be something like square algorithm and square. And let's write it, and after it, using some tricky ideas, we will reduce running time to linear. We can use code like this. Just use definition. I think it's naive method to calculate that function. Initially, all z values are zeros, and let's calculate them from the position 1 to the end of the string. And while we can extend, increase value of z, if this character match this character, if are the same, then we can increase the value z. The microphone is off. I'm sorry about that. Should I repeat everything? No. Does your camera write audio?
Yeah, I will test it over here.
Okay. It works now, right?
Yeah.
Okay. Yes, and it's easy to see that this method runs order and square, and it is slow for us, for sure. Okay. If we have some position L, and z function in this position is strictly greater than 0, then we have picture like this. And this prefix equals to this substring. And the value z here at position L equals to the length of substring. Okay. If we have something like this, and we need to calculate that value for position I, we can be sure that we have position here such that this character is exactly the same as this character. Next character is exactly the same as next character, and so on. And how can we calculate this position? It's easy to see. It's just like I minus L. If this substring equals to this substring, okay, but previously we already has calculated that value for this position. We know it. For example, it could be like this. But if it is like this, do we need to calculate that position here? Because it is exactly the same, right? But maybe that value here is large, like this. Can we use this value as that value for position I? No, but we can use part of it. Which part? Yes, sure. Up to value R. So if we maintain the block LR, sometimes we can skip many calculations, many iterations of this loop, just initializing value Z with some value which is greater than 0. You see? Okay. So our algorithm works as follows. Let's maintain two pointers, L, R, L and R, such that L and R some Z block which matches the prefix of the string, and R is maximal. For sure, we want to maximize R because we use it as upper value to choose value Z. Let's maintain. Initially, we do not have any good candidates for L and R, and we can use, for example, 2 zeros, and it will be some kind of block which is to the left of our position, and we cannot use it at all. And let's do exactly the same things, but use an idea to reuse information which was calculated before. We have exactly the same loop, and now there are two options. If position I is to the right of R, or position I is inside LR block. If position I is right, we can't do nothing. We should use 0 starting value and calculate that function in naive way. But if we are in that block, like here, we can initialize Z of I with some value. Which value? Please tell me. It will be minimum. It will be minimum between two values. The first value is It's easy to look into this z value. It is previously calculated z function at the position which is mirror of our current position in the prefix. And the second value, r minus I plus 1. Because if r and I are the same, we have one character matched. Okay. We initialized that function with some value. And after it, all we can do is just to repeat internal loop with naive way to increment the value to make it actual. Okay, now here we have correctly calculated value of z for position I. But what else we should do? Yes, we should update L and R if needed. And if R is less than the end of this currently found Z block, in this case, we should update values L and R. Okay. I do not use perfect C++ or something else, you see, and actually I do not like on Blackboard to use curly brackets, just indentation. Here, 1, 2, 3, 4, 5, 6, 7 lines is linear algorithm to calculate that function of a string. Actually, it runs in time order of n. It's not easy to see why, but you see that for each iteration of nested loop, we increase value z, and for sure after it, value r will be updated. But could be how often it could be updated? At maximum n times. So internal loop will not make more than n iterations. And this algorithm is linear. Actually, string match, yes.
What is exactly the meaning of the range we maintain? L and M.
Okay, I'll repeat. string S, some position j, and if that value in this position is greater than 0, it means that there is, we call it Z block. This substring is exactly the same as prefix. Look, see? And LR are 2 pointers, and they point to the leftmost and rightmost end of some block previously found, some previously found block. So, for sure, the substring from L to R is the same as prefix of length R minus L plus 1. And among all such blocks, we maintain such block which has maximal possible R. Any other questions about this algorithm? No. Okay. You may think about it as naive algorithm, and we somehow improved it, and it became faster. Mm-hmm.
It's just the same idea of pointer algorithms in code form.
No. It is another 2 pointers.
But it's similar in some way.
No, I don't think. We maintain Z block LR such that R is maximal and use it. We use it in these lines and we maintain it in these lines. Okay, but actually string matching problem is not only the only application of that function. Let's look in some other applications. String matching problem. Let's look into another problem. You are given string S. You are to find the number of different substrings of S. For example, if string S is ABA, C, ABA, our old friend, what is the number of different substrings? Let's calculate them, the number of substrings of length 1. I think 3. 3 substrings of length 1. And we have, I think, 4 substrings of length 2. AB, BA, AC, CA. And we have 4 substrings of length 3. ABA, BAC, ACA, CAB, and so on. And I think in total there are 17 different substrings in the given string. If we will try to use some naive method to calculate them, I think it will be not very fast. We should iterate through all possible substrings and I don't know, for example, put them into the set. And after it, just use size of the set. It will run in at least cubic time, because we have a square number of substrings, and we need linear time to compare to substrings. Strings are not integers. We cannot compare them in constant time. So the running time will be about cube, and it is slow for us. For example, our constraints are about 5 or 10 thousandths, and we can use that function to prepare a solution which runs in square time. Let's do it. We will use some kind of dynamic programming. Actually not. Just add one letter, another letter, append to the string from the right. We will start from the empty string, and we will maintain the answer for it. The answer is 0, right? A. Empty string. Answer is 0. String A. Answer is 1, right? String AB. Answer is how much? 3. You may think about it as a period, 2 more strings. We already have one string A and a period, 2 more strings, A, B, and B. See? And we append 3 here. And let's append letter C to the right of the string. And we have candidates ABC, BC, and C. And all of them were not counted before. And all of them we should add them to the answer. Letter A and another situation. We append the third letter. It is letter A. And we should consider all suffixes. They can increment our answer. Suffix ABA will increment it. Suffix BA will increment it. But suffix A will not, because we have counted it before. Am I right about 5? Yes. Letter C. It's easy to see that letter C. It is easy to see that each suffix wasn't considered before, so we should add 4. Letter A. Also, it's easy to see that almost all suffixes are good, are new, except one. Which one? A. Yes. So 4 suffixes. And so on. Let's look into the situation in general. We have current string, say T, and new character C, appended to the right. And we are interested in such suffixes which cannot be found in the string before. Such suffixes are interesting, and suffixes which were considered before are not interesting for us. But it's easy to see that it is monotonic function. You see, if this function, if this suffix is not interesting, is not new, then shorter suffix is not new too. And in the opposite way, if this suffix is interesting and cannot be found before, longer suffix is interesting too, you see? So our idea is to find the length of such maximal suffix which can be found before. If its length is L, then we can easily calculate the number of new suffixes. It's just M minus L, where M is the total length of all the string. You see? And so our idea is to find value L. And if we want running time order n squared, we can spend linear time to find such value. Let's reverse the string. C and reversed value, the reversed string T. We are interested in such longest prefix now, which can be found in string. You see? But in terms of that function, what should we find? It is maximal value of z. So the solution here is one by one append characters to the right end of string. And each time we should find such value L that suffix of length L can be found before, and L is maximal. And update answer, increase answer by value M minus L, because it is the number of new suffixes, where M is the total length of current string. And value L, we can easily find it. Just reverse the string, calculate that function for it, and get maximal value. The running time is n squared. As homework, you can think about, for example, similar problem where you have to find the total length of all different substrings. Find total length of all different substrings. It is very similar, and you can use the same approach. Another problem, string period. string period. The string is periodical if it can be represented by several copies of another string. I mean string S, AB, AC, AB, AC, AB, AC. This string has period of length 4. And using that function, it's easy to find if given string is periodic, and to find period itself, I mean maximal period for sure, of string. No, minimal period by length. Okay, let's calculate that function for given string. And I give you 1 minute to get the right answer for this solution, how to use that function to find the period. Okay, who has the answer?
First position in the zero rate that has is completely apple.
So we should find such position I, that I plus z of I is n.
Yes.
And we should check that n is divisible by I plus 1, right? So
Is divisible by I.
by I. Yes, it's divisible by I. Yes. And among all such positions, we should use the smallest one. And if there are no such position, the string is not periodical. Okay. And let's use this word. And another example, another application. Search with at most one mistake. The problem is you are given string text T and also you are given pattern P, and you are to find such position I that pattern differs with string in substring in these positions in at most one position. So it is nearly occurrence but not occurrence. Let's look to the example. Does text T contain pattern P in these terms here? What's the answer? Yes, it contains, because you can consider such substring, and it will be at most one mistake in it if you place these pattern under the substring, and so the answer is yes. Okay, and we can use that function to solve this problem in linear time. The first idea will be the same as usual string matching problem. Just write pattern, separator, and the text itself. And let's calculate that function of this string. If we have value equals to length of pattern, then we have exact matching, and answer is yes. So consider that all values of that function are less than the length of pattern. Okay, and let's look into our interesting position here, because we know that this position makes our answer. And what is that function here?
2.
Yeah, that function here is 2. And if we would have something like inverse that function for this position in this side from right to left, the value at least 1 here will tell us that we found the matching. Because if that function in the left end, z of I, and some kind of inverse that function on the right end, I plus length of p minus 1, such that in total they give us length of p minus 1, then it is easy to see that we have exactly one mistake. But how can we find inverse that function? Not inverse, but reverse that function. How can we find it? Yes, we can reverse the string. We can reverse text. We can reverse pattern and calculate that function again. So the solution is to build such string and to build another string, reverse p and reversed text. And if we calculate that function for the first string and for the second string, we can use their values to check this kind of situation and to answer is matching exists from the position I. Okay. I think it's all I wanted to tell you about that function. And let's have some small break, and we will continue after the small break. Thank you. Okay, let's continue. Before start, I'll write my email address. If you have any questions about code forces, maybe about our lectures, you can write me. Please don't publish it in some public places. I already have many incoming letters each day. And also, you see T-shirt on me, and I brought several such T-shirts here, and the best students, which will take part in my contests, they will have, I'll present such T-shirts for them. So maybe it will be some kind of motivation and so on. So I hope contests will be a little more funny after it. Later, I'll count them, and I'll give you a specific number, how many exactly T-shirts I have. Okay. Let's continue. Our next topic is prefix function and Knuth-Meres-Pratt algorithm. Prefix function is something like similar to Z function, but it differs. And actually, I prefer to use one-based indices for prefix function. I think it appeared to be just a little bit more natural if you use one-based indices in it. And think in terms of lengths. I'll show you. Okay, you are given a string S, say our old friend ABA, CABA. Prefix function is such array P. You can use Greek function, Greek letter, that P of I is let's give another definition before. If you have a string, if its prefix is exactly the same as its suffix, we call it border. Border is a such prefix which equals to suffix. And for sure, there are many borders string has. For example, our string has border of length 3, ABA, because ABA is at the same time the prefix and the suffix. AB, is it the border? No, because AB is not the suffix, is not a suffix. And letter A, yes, it is border. And also we can think about empty string as a border also. Okay. Border is such prefix which equals to suffix. Okay, let's return to prefix function, and prefix function is 0 if also border is always about proper strings. So if because string itself is not a border. Okay. And P of I is length of maximal border longest border of prefix of length I. For example, by definition, prefix function of 1 is always 0. Because for single character, the only border is empty string. Okay, let's calculate prefix function for given string. I will write prefix function values under the letters, and they should correspond each other. So here I write 0. Here, for string AB, what is the length of the longest border? 0. If we look into the string AB, the only border is empty string. I'm not sure I understand you. Well, let's continue. And for string containing 3 first letters, ABA, the prefix function is 1. ABAC, prefix function is 0. ABACA, 1. ABACAB, 2. And ABACABA, 3. It's the first example. And for example, string A. Prefix function for prefix function of 1 is 0. It is always 0. Of 2, 1. And 2, 3, 4, and 5. And if we use string AB, prefix function 0. Let's continue. 0 and Y2. 1. Only 1. Because border of string ABA is 1. The length of the longest border. 2, 3, 4, and 5. You see?
Keep the B, the 4th letter.
Uh-huh. Zero. 0, 1, 2, 3, 4, 5, 6. Right? Okay. It is prefix function. We can use it in similar way to solve string matching problem. I'm sorry. Let's use it. If we have pattern P and text T, we can build new string P separator and text T as we did it before. A, B, C, I do not remember. And calculate prefix function for new string. And if that function points to the starting positions of occurrences, prefix function points to the ending positions. If we look at this position and if we look at this position, we can easily see that prefix function here and here, both values equal to 3. And if the value of prefix function equals to the length of pattern, then this position is the final position of some occurrence. Great. So we can use prefix function, something like that function, but right now we do not know how to calculate it fast. There are some interesting properties of prefix function. Let's look on some of them. Look at this example. We have a segment of grow of prefix function. 0, 1, 2, 3. Okay, and question, is it possible that prefix function grows faster than by 1 to the next position? Can it be, for example, 0, 2, and 4? Yes, the correct answer is no. Look. Look on two neighboring positions, I minus 1 and I. If we have border of length L which ends in position I, then we have border of length IL minus 1 finishes in position I minus 1. You see? So by contradiction you can easily show that if prefix function grows, it grows not faster than by 1 to the next position. In other words, this condition holds. Okay. Another property. Let's look on the position I, and the value of prefix function p of I is positive. So it means that this prefix is equal to this substring. Okay. But let's calculate P of I. What is P of I? It's easy to see that P of I is this position. You see? It is P of I. And P of I, it is the length of the longest border of this prefix. But this prefix is exactly the same as this substring. So P of I is also the length of some border. It is not the longest, but it is the second by length. And we can iterate it again and again. If we calculate P of I, it will be one more border, and so on. If we iterate value of prefix function, we iterate through all possible borders in order from longest to the shortest. And it's not in infinite sequence, you see. It breaks if the value became 0. So you can write P of I, longest border, length of longest border, P of I, the length of the second by length border, P of I, third border, and so on. Okay, all these properties will help us to build efficient algorithm to calculate prefix function. And let's do it. Let's calculate prefix function from left to right, and we can imagine that we already have calculated all values before position I, and we are in the position at the position I, and we want to calculate it. And it is always good only in programming contests, in solving programming problems, to be greedy. Let's feel greedy. Let's wish to be value as greater as possible. What highest value it could be? Previous value plus 1. It cannot be greater. What is previous value? Previous value, it is some value of prefix function. And we know that this substring equals to this substring. But in what case the value at position I will be greater by 1? If this character is exactly the same as this character. If they are the same, we can extend previous border by 1, and our new value will be previous plus 1. But it is possible that it's false. But we are still greedy. What border we will try again? We will try the second by length border. We can use another border and compare another two characters. This character first after border and character at the position I. Again, if they are equal, then the value at the position I equals to the length of border plus 1. If not, what should we do? Continue again, and again, and again, and again. And for example, we can stop because there are no more borders. Nothing special. We should just check if the zeroth character is equals to the character I. If they are the same, then the value equals to 1. If they differs, then the value of prefix function here is 0. Now let's write the code. Okay. We go from the second position to the right. I remind you that I use one-based indices for prefix function, and it is natural here. Okay. And to begin, I initialize the value in the position I with the value in previous position. Just something like this. Okay. And now I'll try all possible borders from longest to shorter with hope to extend them. While I have valid border P of I greater than 0. It means I have length of valid border written in P of I. And characters do not match. What character? Character at the position I and character at the position P of I. Because it is we have very simple form because string in 0-based indices and P is 1-based indices. S of P of I not equal to if the length of border is P of I, the first character outside border has exactly this position. And what should I do in the body of while? Please help me. This condition means that I have border, but it's not good. I cannot extend it. I should replace the value of prefix function of current border, which is written in P of I, to the next border. I just go to the next border, shorter. It's shorter border. Okay, and now we have just one option. If we can extend our border or not. Let's check it. If we can, I have one mistake here, -1, and here you should have -1 because of 0 indices in string. If we can extend it, we should increase the value by 1. If we cannot extend it, it means that the value actually is 0. Because non-zero value should be iterated again and again before. And that is the complete code how to calculate prefix function. Okay, let's go to some applications, more applications. All of you have heard about Knuth-Morris-Pratt algorithm to find substring in text. Yes?
Is it possible to have a border overlap?
I forgot about opportunity to move them up, so and one item also. This algorithm works in linear time, and also it's not easy to see why it is in linear time, but see, look. Each time when internal while has iteration, the value of p is decreased by at least 1. Each iteration of nested while decreases the value p on at least 1. From the other hand, if it increases by at most 1 on each step. So in total, it can increase for at most n to value n. So it cannot be decreased more than n times. So nested while works at most n iterations. And do not look that we have 2 nested loops. The total time complexity is linear. Okay. And Knuth-Morris-Pratt algorithm. I can continue here. Let's return to our method to use prefix function to find substring in text. Pattern, separator, and text. And we calculate prefix function for the whole string. Actually, look here at the position I. For sure, every value of prefix function is not greater than length of pattern. For it is correct for any position. And it means that calculating the value of prefix function here, the first iteration of while moves value to the left from separator, because this expression gives us value not greater than length of p. I mean that actually we do not need for calculations here the values of prefix function. We do not use them. We just use previous value. And in case of at least one iteration in while, we jump to the values which correspond to the pattern. So if we do not use them, we can not to store them. And we can only build real prefix function and store it in memory, in computer memory, only for this part of string. And this part of string doesn't use it. Okay. And if so, we can think about the second. So Knuth-Morris-Pratt algorithm has two phases. Phase 1 and the first phase and the second phase. On the first phase, it calculates prefix function of pattern P. On the second phase, it iterates through text and maintains value of longest prefix, the length of the longest prefix of P, which ends in current position. It will look like exactly, code will be exactly the same as to calculate prefix function. But it is better to think about it as maintaining special value. Again, we calculate prefix function of pattern. And now we will maintain special value k. Initially it is 0. The value k is, if we are in the text at the position I, k is the length of the longest prefix of P, which ends at the position I. And if at the position I there is occurrence of pattern, then the value k equals to length of P. And it is less in other cases. Actually, k is exactly the same as the value of prefix function of combined strings. You see, it is exactly the same. But actually, it is some kind of better to think about it as in these terms. Okay, let's try to do it. We just iterate through the whole string. Okay. We go through text from left to right, and we should maintain the k. We know the previous value of k, and we want to, if within greedy, exactly the same as in prefix function, we can extend by one character the previous value, so increase k by 1. But if we cannot do it, we should consider the next smaller border and so on. Let's do it. While k is valid and prefix of k not equals to the current character of text, we should consider the smaller matching, smaller prefix which ends the position I. And exactly the same idea, let's check that we actually can extend our matching if P. No. P. What's wrong? I think it's correct. Okay. You afraid me. And it is nested in the main cycle, in the main loop. Okay. Actually, this code is exactly the same as computation of prefix functions for whole string, and just do not store exact values of prefix function for this part. From the other side, on the other hand, it maintains special value k, the longest matching of prefix of p, which ends at the position I. Okay. Why Knuth-Morris-Pratt is better than just our simple way to find to solve the problem? Why this method is better? Yes, because of memory. Consider typical case. You have not very long pattern, but huge texts. One more thing. This algorithm processes text character by character in online mode. We do not need text, the whole text before processing the request. We can think about it as we have some kind of stream, and we pick one character, next character, and so on from the stream, and all the state of our computation is just one variable k. You see, it is very important to try to think about Knuth-Morris-Pratt, I mean the second phase, as finite state machine. The state of this machine is the value k. And when we have one more character, I mean t of I, the state changes. And it changes only depending on character and previously calculated prefix function. So it is exactly finite state machine, but written not in compact way. We do not have right now the matrix, the function from state cross character to new state. But we will do it later. Yes?
K can be equals the length of B.
K is from 0 to length of P.
It cannot overflow.
Yes, it cannot overflow by construction. It is always in bounds from 0 to maybe you should here check it. Or, for example, in practice, it is always good idea to append to the pattern separator character. And yes, maybe it was a good question. To avoid some overflow here, it is good idea to make something like P plus equal separator character before any computation. And after it, value k will be strictly less than new length of P. Okay. If we look into the same problems as for that function, they all can be easily solved by prefix function as well. For example, if we want to calculate the number of different substrings, we can do exactly the same approach. And remember, we need the maximal length of such suffix which can be found inside string previously. And what we did, we reversed the string, calculated that function, and looked on the maximal value. And here exactly the same situation, because the maximal value of prefix function is always equal to the maximal value of that function. So for many problems, you can decide by yourself, do you want to use that function or do you want to use prefix function? Actually, we have one-to-one mapping between them. You can reconstruct prefix function from that function in linear time and vice versa. But actually, many times I saw problems then in which that function is more natural than prefix function and vice versa. It's not always easy to change one to another and so on. Okay, let's continue this finite state machine approach. And And I want to build matrix to correspond to the transitions function of this finite state machine. I want to have matrix where these rows which correspond to states, it is values of k. And columns correspond to alphabet sigma. Sigma is just alphabet of text. And it will be new states on intersections. Okay, how can I do it? Small example. If our pattern is A, B, A, and separator, let's look on some transitions. For example, A, 0, A. What does it mean? It means that current state is so that at our position I, there is no positive length prefix of P which ends in this position. No matching. And after this, we've got new character A. What can we say about new matching lengths? What's length of new matching? Okay, one more again. The current situation is that we have some text, character by character, one after another. X, Y, Z. And we came to this position, the after position Z, after position containing the letter Z. Do we have any prefix of P matching this position? Do we have it? What the length of maximal prefix of P which ends in this position? 0. It is 0. And our state is 0. And after it, we've got letter A. And what our new situation, our new state? What is, yes, sure, it is 1. It means that now, after 0 matching, if we append letter A, our matching will have length 1. Okay, another example. A, 1, B. It means that we had some part of text and we are not interested in it actually. Some text, some characters, and so on. But we know that in current position, we have matching of length 1. So in current position, last one character is exactly the prefix of length 1 of P. And after it, we've got new character B. What can we say about new matching? What's the length? Yes, it is 2. And what about A of 1 of A? 1. It means that we should drop our previous matching and start new matching. It is 1. And another example. A, 3, B. It means we have some part of text and we are not interested in concrete characters. But we know that it ends on ABA, last 3 characters. ABA, because our state is free. And the first 3 characters of prefix are ABA. And after it, our new character is B. What our new state? 2, right. Our new state is 2. And this code do exactly the same things, but it doesn't build A in a clear way. And let's build it. The zeroth row of A is special because it means that we do not have any matching. How can we build it? We should iterate through all characters of the alphabet. And what about the value A, 0, C? Yes, it is 1 or 0, but what case, what condition should be held if it is 1? C should be equal to the leftmost zeroth character of P. I can write something like this. Okay. Let's continue in general case. Now we are moving through rows from first to the last. We are moving through rows and through characters of alphabet. And there are 2 cases here. Can you describe them? Okay, we already have matching. It is prefix, and the length of matching is I. And our text has exactly the same substring, and here is the next character. The next character is in these terms, what name? C. Right. It is C. And what is interesting case? Yes, C equals to P of I. If C equals the ith character of pattern, then what should we do? A, I, C equals to what value here? I plus 1, exactly. We increased the matching. Else, and I continue here. Else. Else. If they do not match, look, we should consider next border here. Next border here and here. They are equal. They're equals. They're equals. Equal. But how can I find them? I should just use prefix function calculated for P and its value in position I. P of I mean the value of prefix function, P of I, is the length of the next shorter matching. And this shorter matching, we want to extend it in the similar way. You see? But here we have dynamic programming because P of I is less than I. And we already calculated its value. So A IC equals to A P I C. It's done. And now we build automat in classical way. We have matrix which contains transitions for given state, given signal, new state. Okay, how can we use it? Let's look on the following problem. This problem can be solved in some other ways. But this way is very general and can be adopted to solve another problems. Welcome our old friend gray string. Zeros gray string is empty string. Gray string, the first gray string is A, and so on. A, B, A. A, B, A, C, A, B, A. A, B, A, C, A, B, A, D, A, B, A, C, A, B, A. As you can see, they grow very fast, such as powers of 2. And our problem is we have string S, not very long, for example, 1000, and value K. I do not know exactly, but consider it is less, not greater than 1000. And we should find how many times string S is contained in kth gray string. We cannot use any kind of naive solution because this string is very huge. And we should use something more interesting, right? Okay. Let's build another matrix, or you can think about it as finite state machine. These having the following properties. Currently we have state. The state is our matching, as usual. What we have? We have something like it. String S, separator, and our huge gray string. And we can use approach with finite state machine. Just build finite state machine for S plus separator. And after it, in some kind of naive approach, we can use character by character from GK and maintain our state. If state equals to initial lengths of S, then it is matching, right? But because of structure of gray strings, we can make some kind of big jumps. Let's do it. Let's build matrix F and I is the length of matching. It is our state. It is state of our finite state machine. And G means that we put to the input of the finite state machine complete string, this string, G of J. And how can we build this? It is easy to see that if this argument is 0, nothing changed. It's just I. The state doesn't change. But if the second argument is positive, it means that we should go through gray string of less order, previous gray string. After it, we should apply one character, and after it, we should apply gray string of previous order again. It is just because of definition of gray string. And how can we do it? Let's do it. F I J minus 1, we applied this part. Okay, after it, we should apply one character, character J. What matrix should we use to apply it? Single character. Yes, it is matrix A. We calculated it before. It is automat for string S plus sharp. So A from F I j minus 1 j. Let's call it x. It is some intermediate state. And our actual state, what should we do else? Yes, we should apply this part of gray string of less order. It is just one lookup to the f x j minus 1. It is the return value. So it is just two nested loops and few ifs, and we can calculate such jumps transition table, which can help us to move through gray strings. One thing you should note that it is better to change the order of dimensions everywhere for f, because we look into we depends on previously calculated values where j is less. You see, here we need calculated values where j is less. So it is better to change the order of dimensions, or you can go through matrix not row by row but column by column, but it is bad because of cache misses, and your program will work slower. Okay, but it is not the solution of our problem, right? Because we need the number of events when state equals to initial length of s. Let's calculate it. Okay. It means the current state is I, and we apply it G indexed J gray string to this state. State I, applied this string, and this matrix contains the number of events, the number of times when state became equals to length of s. If we build this matrix, the answer on our problem is just one cell. What cell? It is k from what our initial state. If we didn't use any characters, it is 0. It is 0. We have 0 matching. It is 0 matching. And what string won't we apply? It is gray string of order k. So by definition, this value is the answer on our problem. How many times string s is contained in kth gray string. Okay, let's calculate this value using the similar idea. If the second argument equals 0, then I think the result is 0. It means that we didn't get any new matches. But if the second argument is greater than 0, we also have 3 parts in our path. The first path is just to apply the string of less order, right? After it, we will be in state f I j minus 1. You see? And after it, we apply one single character. Just use this x. And we have a question, if this x equals to length of s or not equals. If this x is equal to length of s, it means that we should add 1. Because in the middle, there is one new occurrence. And after it, we should go from state x using the gray string of less order. And we can use calculated before number of occurrences, events in it. K, x, where x is exactly the same. We will have very, very similar solution if we change, for example, gray strings to other regular strings. We always can make such matrices and use them to calculate special values. And here we used finite state machine of Knuth-Morris-Pratt algorithm. We built jumps table F, and also we built table K to count the number of matches if our current state is I and we apply string, gray string of order J. I think that it's all for today. Am I right that it's correct time to finish? I'm not sure about schedule. Or we have more time? How many? Half of an hour. Okay, 5 minutes break and we will continue with some other topics.
It's a dynamic programming, right?
Yes, it's dynamic program.
The dynamic program gives us the answer of this problem.
Yes, because answer, it is this value is answer.
This is the state of
Zero? You mean zero?
and the constraint of the.
Both of them.
This is the state of F automaton and K. What's K?
K is the variable from the statement. There was a question about what is K here. K is a letter from, is a variable from the statement. Our statement was how many times string S is contained in this gray string. And also, as I told you before, it is good idea to change dimensions for array K as well as for F to be sure that calculating it in usual way, two nested loops, we always use previously calculated values to calculate new value. Okay, any other questions about this idea? Yes?
The meaning of I in this statement.
The meaning of I is the same here, here, and here. It is the length of matching. It means that in current state, the last I characters of text are exactly the same as first I characters of string S. And I is maximal. Any other questions? Yes?
The one is K, 7K, not K, size of the S, K.
Here K is capital and here, look. Zero? Why zero? Why zero? Because before we applied any string, our current state is 0. we do not have any matching. We have zero matching. And we have zero matching. And after it, we applied gray string of order k. Any other questions? Yes?
Could you please explain again the meaning of X?
Meaning of X. Okay, I'll use this keyboard. I'll draw an example. Let's look on G4. It is Abatsaba, Dabatsaba. Or it is G3 plus D plus G3. Okay. What is F? Currently, we are in state that last I characters of processed text are exactly the same as first I characters of string S. And after it, we append to it, for example, G4. And the question is, what will be our new matching after we will process all characters from G4? It will be different. It will be some new value. What it will be? Let's calculate it. G4 contains 3 parts. The first part is G3, middle part is letter D, and the rest G3. Using dynamic programming, we know what will be the next, will be the state after processing G3. It is just F I 3. It is our new state. After it, we should apply one single character. And one single character we can apply using table A. Table A is finite state machine. How our state changes if we append exactly one character to the right. And we use these matrix A. X equals A from what state? Before processing letter D, our current state is this F I 3. And our character to process is D. And X is our new state. It is X. And what we need is to apply the rest of gray string. It is G3. And we apply it to state X. Let's do it. And we can write that F I 4 equals to F X 3. This value. So the order of computations is following. The first, calculate prefix function of S plus separator. using the calculated prefix function, we can calculate matrix A. Matrix A is a finite state machine for transitions by one character. After it, we can, using two nested loops, calculate at the same time matrix F and matrix K. And these calculations use matrix A to find intermediate state X. And after we've calculated matrix K, our answer is in K, 0K, lowercase. You see? If you do not understand something, for example, we can we plug my laptop to projector and I can write the solution? Let's do it. Because I do not think that we have enough time to start some new topic, but I do not see great understanding in your eyes right now. And we should move it down.
I should move it down. Just want to know how.
It was this.
Yes. Just check the channel.
I'd like to tell you that I didn't solve this problem before. It is complete improvisation here. Let's try it again, and you can show me on mistypes and something like this if I will have them. No, not my laptop. Maybe another cord?
Can you put it here? Just one more.
Can we? I'll make font larger. What question?
Can you give us the list of the problem to solve it? Is there code force the same problem?
It is not from code forces.
You have the
Let's write the solution together and ask the question after it, okay? I'll make greater font. Okay, what we have, I use streams to read. We have string S, and also we have the value K. Also, what we need to append special character to S. After it, let's calculate prefix function. As I told you, prefix function. I'll write separate function to calculate it. Okay. It is the same as I described it the current value of prefix function is copied from the previous value, and we're trying to find longest border that we can extend. And if we actually can extend it, we increase the value. Okay, I think it is prefix function. Now after it, let's build finite state machine. Finite state machine. For sure, alphabet of lowercase characters is enough. It's no problem if it can be larger, but no problem. Okay, zero. Yes, we used k up to 1000, and it's not enough. But let's reduce our constraints to 24. Because I do not know how to deal with characters greater than z. Okay. Yes?
Do you have to access the table with the hash character? One additional column would be needed? The symbol, the separator. Do you need one more column in the table for the separator?
I used, I do not need it. Because I do not have transitions using this character. No, I do not need it. And the zeros row of transition table, as I told you, it is just something like this. Okay. And other rows, I'd like to change it to C. And other rows, something like this. And there are two cases, as I told you. The first of them, if S indexed with and opposite case. No, not. I think something like this. And all we need is more two nested loops to calculate f and k. I'll replace order of their dimensions. So let's do calculations. We need to, the first dimension is order of gray string, so we need it up to k. K is given in our constraint, in our input. And the second is we call it J. And I is our state. And let's calculate it. We need calculate x. If we have empty gray string, the state doesn't change, and also k is 0, no new matchings. And else we can calculate intermediate position. And here we have f minus 1i. It is intermediate position, and after it f j I is just to apply to this intermediate position gray string of less order. And all we need also is to calculate k. It is just the sum these and also these, because we've appended one character to S, I reflected it, and also and all we need is to write the answer. Also, for sure, k could be a huge number, maybe in your constraints, and you need maybe some big integers or modular arithmetic. It is an example of solution. I do not think it will work. What mistakes? We do not have any namespace, yes. What else?
Sum the character A part of text. Yes. Subtract the character A from the when you're using the string.
For function? Yes, function name. PF. What's wrong? Solution main. And here? C. The first
for loop.
I see.
You have S0 character A.
C small A.
C plus
C plus
Here, yes, sure. Something like this. Maybe the similar thing here. Anything else? Because of large font, I do not see most. Warning, P, C++, what is it? Maybe it was Russian C, I don't know. No, I here should be. At least it is compiled. No, it doesn't work. I'm pretty sure that we can change 5 lines, 3 lines, and it will work. My goal was to show you the almost complete solution of this problem. And I hope that this will help you to solve problems like this in future. Okay? If you are interested, we can together change maybe 1 or 2 lines, but I think it's time to eat. Right? Thank you for your attention, and see you tomorrow in this time, and good luck on the contest.